Grid weak versus strong. The terms weak or strong are often used to describe the grid, but they are rarely explained. A strong grid, from a load perspective, means a connection with low Thevenin impedance or a direct link to the sources feeding it. The Thevenin impedance at a load represents its connection to all generators. Conceptually, it is like a representative fictional generator feeding the load through an impedance that represents all transmission paths. If the Thevenin impedance is low or the load is close to generation, the connection to the grid is strong. A strong connection provides steady voltage that doesn't vary much with load, power factor, or reactive capacitive current. The generators can be viewed as voltage sources, and the closer the load is to the source, the stronger the voltage is maintained. Conversely, a weak grid's voltage will tend to fluctuate with the load. Another characteristic of a strong grid is its ability to provide significant phase fault current, while a weak grid cannot refer to phase current, not all fault current, because a strong connection has low positive sequence impedance. Normal power flows are balanced, and a strong connection has low Thevenin positive sequence impedance. The grid's passive elements, like transmission lines and transformers, keep the negative sequence impedance the same as the positive sequence. Phase faults involve positive and/or negative sequence impedances. A strong grid connection by default means the phase faults will tend to be high. Ground faults can be impacted by positive and negative sequence impedances but are often limited by the Thevenin zero sequence or ground impedance. Few spots on the grid have ground sources delta Y or zigzag transformer connections on a solidly grounded grid. On high impedance or ungrounded systems, the grounding impedance, or lack thereof, completely limits ground fault current. Relaying engineers often refer to weak and strong connections based on available phase fault current. Load step-up transformers are usually specified with impedance to reduce available phase fault current at the expense of voltage regulation. Transmission and distribution planning engineers are more concerned with positive sequence impedance when describing a system as weak or strong because they are more concerned with feeding load than faults. Grounding's impact on ground fault current is becoming clouded as inverter-based sources need to be programmed to supply negative sequence current so that ground and unbalanced faults can be fed fault current. If the inverter is not programmed to supply, or is limited in supplying, negative sequence current, the fault current could be restricted by inverter-based generation, not by how the system is grounded. This is very different from synchronous generation. Strong grid systems invest heavily in the latest technology and materials for building power plants, transmission lines, substations, and distribution systems. They use advanced high-voltage lines such as HVDC for long-distance transmission, which significantly reduces losses and can carry large loads. Strong grids have well-funded and organized maintenance schedules, preventing failures through regular checks and preemptive repairs. Weak grids often rely on older, inefficient, and outdated infrastructure, which leads to high transmission losses and frequent equipment failures. Weak grids may use low-voltage lines, which are prone to losses and overloads, particularly when the demand spikes. Repairs are often done only after failures occur, resulting in prolonged downtimes and inconsistent power supply. Strong grids use sophisticated systems like SCADA, Energy Management Systems (EMS), and Distribution Management Systems (DMS) to monitor and regulate voltage and frequency in real time. They use devices such as transformers with tap changers and capacitor banks that automatically adjust voltage levels to maintain stability. They can handle fluctuations in demand and supply due to high penetration of renewables and distributed generation. Weak grids often experience significant voltage swings, leading to equipment damage, inefficient energy use, and even power outages. Weak grids may not have the technology or resources to continuously monitor and control voltage and frequency. Manual interventions or outdated relay systems are more common, increasing the risk of instability. Due to limited infrastructure and fewer technologies in place, weak grids struggle to cope with variations in demand, renewable energy integration, or even minor faults. Strong grids have multiple, interconnected pathways for electricity transmission and distribution, meaning that if one line or substation fails, power can still flow through other routes. This reduces the likelihood of widespread outages. These systems are often designed with an N-1 principle in mind, meaning that the grid can still function even if one key component, e.g., a generator or transmission line, goes offline. Strong grids experience fewer interruptions due to redundancy, advanced maintenance, and reliable equipment. In weak grids, a single fault in the transmission or distribution system can often lead to cascading failures and large-scale blackouts because there is no alternative route for the power. Weak grids usually lack the capacity to continue operating after losing a critical component, leading to outages that affect entire regions. Due to lack of redundancy, weak grids have a higher mean time to repair (MTTR), resulting in frequent, prolonged outages. Strong grids are often transitioning toward or have implemented smart grids, or automated systems, real-time data, and advanced communication networks such as the Internet of Things are used to optimize performance. Technologies like automated feeder switches, intelligent fault detection systems, and grid-tied energy storage allow the grid to respond instantly to changes or faults. Strong grids incorporate DSM technologies that allow for real-time response to changing demand, shifting consumption away from peak times to reduce strain on the grid. Weak grids often rely on manual processes for many aspects of grid operation, including fault detection, load balancing, and maintenance, which increases response times and the likelihood of human error. Without technologies like smart meters or SCADA, weak grids have little visibility into what is happening at different points in the system, making it difficult to optimize performance or prevent issues. Weak grids lack the infrastructure for effective demand-side management, leading to frequent overloads during peak periods, as they cannot shift or reduce demand dynamically. Strong grids incorporate a wide range of energy sources, including fossil fuels, nuclear, hydro, wind, solar, and geothermal. This diversification provides energy security and reduces dependency on a single source. Strong grids have the ability to integrate large amounts of renewable energy while maintaining stability, thanks to grid upgrades, storage technologies, and efficient grid management practices. Strong grids tend to have robust domestic energy production and, when necessary, trade energy with neighboring countries to secure supply in times of shortage. Weak grids often rely heavily on a single or few energy sources, such as coal or hydropower. A drought, fuel shortage, or technical failure can cause severe power shortages. Weak grids lack the flexibility to incorporate significant amounts of renewable energy, as they often don't have the technology or infrastructure to manage intermittent supply like wind and solar. Weak grids may rely heavily on energy imports, making them vulnerable to geopolitical tensions, price fluctuations, and supply interruptions. Strong grids use highly responsive protection systems, such as differential protection, distance protection, and automatic wreck losing systems, to isolate faults quickly and restore service. Strong grids are designed to handle disturbances such as short circuits or equipment failures without significant impact on grid stability. Strong grids employ real-time fault location technologies, reducing repair times and minimizing the impact of outages. Weak grids may only have rudimentary protection systems that are slow to detect and respond to faults, resulting in more widespread outages. A single fault can destabilize a weak grid due to insufficient fault isolation and recovery mechanisms. In weak grids, fault detection is often manual and slow, leading to extended outages while crews work to locate and repair the issue. Strong grids are designed with climate resilience in mind, with transmission lines, substations, and generation facilities engineered to withstand natural disasters such as hurricanes, floods, earthquakes, and extreme temperatures. After a natural disaster, strong grids have emergency protocols and resources including mobile generators and fast repair teams to restore service quickly. Weak grids are often poorly equipped to handle natural disasters, with aging infrastructure more likely to fail under extreme conditions. Recovery from natural disasters can take weeks or months in weak grids, due to limited resources and inadequate emergency response plans. Strong grids benefit from economies of scale, efficient power generation, and low transmission losses, reducing operational costs for utilities and consumers. Stable electricity supplies promote industrial growth, attract foreign investment, and support technological advancements, all of which contribute to robust economic growth. Due to high efficiency, diversified energy generation, and reduced system losses, consumers and businesses experience lower electricity prices compared to those in weak grid systems. Investments in grid modernization, automation, and smart grid technologies yield high returns by improving efficiency, reliability, and reducing maintenance costs. Weak grids are plagued by high transmission losses, frequent outages, and inefficient power generation systems, which result in higher operational costs. Industries and businesses suffer from unreliable power, leading to decreased productivity, higher operational costs, and reluctance from foreign investors to invest in regions with weak grid reliability. Due to inefficiencies, maintenance costs, and reliance on backup generators in the absence of stable power, electricity prices tend to be higher. Investments in weak grids face low returns because of inefficiencies, lack of proper regulation, and outdated technology that quickly deteriorates, requiring further costly investments. Strong grids often have a diversified energy mix that includes a significant share of low-carbon energy sources like renewables, solar, wind, hydro, and nuclear. This helps reduce the carbon footprint of electricity generation. Strong grids promote energy efficiency through better transmission, demand-side management, and energy-saving technologies like smart meters and sensors. By efficiently integrating renewable energy sources into the grid, strong grids can reduce the dependence on fossil fuels, helping combat climate change and environmental degradation. Strong grids can invest in technologies that monitor and control emissions from power plants, ensuring compliance with environmental regulations. Weak grids often rely heavily on fossil fuels, especially coal and diesel generators, leading to higher carbon emissions and contributing significantly to air pollution and global warming. Poor infrastructure and lack of advanced energy-saving technologies result in inefficient energy use, which increases the overall environmental footprint. Weak grids struggle to accommodate intermittent renewable energy sources like wind and solar, due to a lack of grid flexibility, storage systems, and grid management technologies. As a result, they rely more on polluting fuels. Weak grids often lack the financial resources and technical capacity to install emissions control technologies in power plants, leading to increased environmental harm. Strong grids are designed to accommodate the intermittent nature of renewable energy sources. They use technologies such as energy storage systems like batteries or pumped hydro, demand response programs, and real-time grid balancing. Strong grids can integrate large amounts of renewable energy without sacrificing stability, allowing countries to meet renewable energy targets and reduce their reliance on fossil fuels. Sophisticated energy management systems enable real-time tracking of renewable generation and grid demand, optimizing the supply from renewables when available and ensuring stability during fluctuations. Strong grids incorporate energy storage solutions, which are critical for managing the variability of renewable energy, such as balancing supply during periods of low wind or solar output. Weak grids face challenges in integrating renewables due to their intermittent nature and lack of grid flexibility. This results in continued dependence on conventional fossil fuel generation. Weak grids often lack the financial and technical resources to invest in large-scale energy storage solutions, making it difficult to store surplus renewable energy for later use. Because of frequent outages and voltage fluctuations, weak grids find it challenging to handle the variability of renewable energy, which can further destabilize the system. In weak grids, renewable energy sources are often curtailed i.e. turned off because the grid is unable to absorb excess power, which wastes renewable energy potential. Strong grids are often interconnected with neighboring countries or regions, which provides multiple benefits, such as increased energy security, the ability to trade energy, and better management of peak loads and renewable energy. Countries with strong grids can engage in cross-border electricity trade, buying and selling power to optimize costs, and efficiently manage supply and demand fluctuations. Many countries with strong grids participate in regional power pools e.g. the European Network of Transmission System Operators for Electricity, ENTSO, which increases system stability and resilience. Interconnected grids can share renewable energy resources, ensuring that surplus renewable energy from one region can be distributed to others, maximizing the use of clean energy. Weak grids are often not connected to neighboring countries, leading to limited access to additional power resources and making them more vulnerable to local power generation shortages. Weak grids lack the infrastructure for cross-border energy trade, missing out on the economic and stability benefits of sharing power with neighboring countries. Efforts to integrate weak grids into regional power pools can face technical and financial obstacles, as the infrastructure may not meet the standards required for interconnection. In some cases, weak grids may rely heavily on electricity imports from neighboring countries to meet their demand, which creates energy security risks and increases vulnerability to supply disruptions. Countries with strong grids have robust regulatory frameworks that promote investment in grid modernization, renewable energy integration, and energy efficiency initiatives. Regulations ensure fair market competition, grid access, and reliability. Strong grids benefit from clear government policies that set ambitious targets for renewable energy adoption, grid resilience, and carbon reduction, providing long-term stability for investors. Governments in strong grid countries often provide incentives such as tax breaks, subsidies, or grants for research and development R&D in smart grid technologies, energy storage, and renewable energy. Regulatory authorities enforce stringent reliability and quality of service standards, ensuring that utilities maintain high levels of service. Countries with weak grids often lack clear, enforceable regulations for grid maintenance, renewable integration, or energy efficiency, which leads to underinvestment in grid infrastructure and modernization. Weak grids may suffer from frequent policy changes or lack long-term planning, which discourages investment and hinders grid development and expansion. Governments may lack the resources or political will to provide adequate incentives for grid modernization, resulting in continued reliance on outdated infrastructure and technologies. In weak grid systems, there may be insufficient enforcement of reliability standards, leading to frequent outages and poor service quality without consequence. Strong grids are at the forefront of grid modernization, with widespread deployment of smart grid technologies that enhance real-time monitoring, improve efficiency, and allow for dynamic load management. Strong grids are increasingly moving towards a decentralized energy model, where distributed energy resources such as rooftop solar, battery storage, and microgrids are integrated into the main grid to increase resilience and flexibility. Many strong grids are adopting advanced digital tools and platforms such as artificial intelligence, machine learning, and blockchain to manage grid operations more efficiently, predict demand patterns, and prevent failures. Grid modernization in strong grids often includes efforts to enhance cybersecurity, protecting the grid from digital threats while building resilience to physical disruptions like natural disasters. Weak grids often lag in modernization efforts due to financial constraints, limited technical expertise, and a lack of political or regulatory support for advanced technologies. Weak grids typically rely on centralized power generation and lack the flexibility to incorporate distributed energy resources, which limits their ability to modernize and become more resilient. Digitalization efforts in weak grids are often minimal or non-existent, due to a lack of infrastructure, investment, or technical know-how. Without the necessary investment in cybersecurity, weak grids are vulnerable to cyber attacks, which can further destabilize already fragile power systems. Consumers in strong grid systems enjoy uninterrupted power, allowing households, businesses, and industries to operate without worrying about outages. Reliability is a key factor in improving quality of life and economic productivity. Because of the reliability of strong grids, consumers face fewer costs related to power outages e.g. productivity loss, equipment damage, or backup power expenses. Strong grids maintain consistent voltage and frequency, minimizing power quality issues like sags, surges, or harmonics that can damage sensitive equipment. In a strong grid, consumers often have more options for energy providers and can participate in programs like demand response, time of use pricing, or community energy programs. Consumers in weak grid systems endure frequent blackouts or brownouts, severely disrupting daily life and business operations. Backup generators are often a necessity. Downtime caused by outages in weak grids leads to high costs for businesses and households, including lost productivity, equipment damage, and increased generator fuel consumption. Weak grids often struggle to maintain consistent voltage levels, causing voltage sags and surges that can damage electrical appliances and industrial machinery. Consumers in weak grids may have fewer options for selecting energy providers or participating in innovative programs that help reduce costs or increase sustainability. Strong grids are characterized by advanced technologies and well-maintained infrastructure that minimizes losses during transmission and distribution, typically below 5%. Strong grids often support large-scale energy efficiency initiatives, incentivizing consumers and industries to reduce consumption through improved building standards, energy-efficient appliances, and industrial upgrades. Grid optimization technologies like voltage control, reactive power compensation, and phase balancing reduce the amount of energy wasted and ensure maximum efficiency of energy flow across the system. Strong grids maintain a higher capacity utilization rate, meaning that existing infrastructure is more effectively used to meet demand without overbuilding. Weak grids often suffer from technical and non-technical losses e.g. theft, poor maintenance, low-quality equipment, which can exceed 10 to 20%, resulting in a significant waste of generated electricity. Energy efficiency programs are rare in weak grids due to lack of funding and regulatory support. Outdated appliances, poor insulation, and inefficient industrial processes are common, leading to higher energy consumption. Weak grids lack the technical capability to optimize energy flow, leading to imbalances in supply and demand and further increasing losses. Weak grids often operate well below their potential capacity due to inefficiencies, leading to wasted resources and the need for frequent infrastructure repairs or upgrades. Strong grids often operate in liberalized energy markets, where multiple providers compete, fostering innovation, lowering prices, and improving services. These markets promote efficiency and integration of renewable energy. Strong grids support wholesale power markets where electricity is traded in real time or through long-term contracts, creating efficient price signals and ensuring that electricity supply meets demand cost-effectively. In strong grid systems, market mechanisms exist to trade ancillary services e.g. frequency regulation, spinning reserves, ensuring grid stability and reliability. Consumers in strong grids can often choose their energy supplier, leading to better customer service, innovative pricing models, and increased competition among utilities. Weak grids are often dominated by state-owned utilities or a single provider, limiting competition and innovation. Prices are typically regulated, and consumers have little influence over service quality or pricing. In weak grids, there is limited or no capacity for wholesale power trading due to the lack of market mechanisms and poor grid connectivity, which stifles competition and cost efficiency. Weak grids may lack the infrastructure to support ancillary services markets, making it harder to stabilize the grid and maintain reliability. Consumers in weak grids typically have no choice in energy suppliers, reducing incentives for utilities to improve services or invest in new technologies. Strong grids employ a well-trained workforce that is capable of operating advanced technologies, performing complex system analyses, and maintaining the grid. Continuous education and training are common. Strong grids benefit from extensive R&D efforts that drive innovations in grid management, renewable energy integration, and energy storage. Strong grids often participate in global knowledge transfer programs, sharing best practices, collaborating on grid modernization efforts, and improving technology adoption worldwide. These systems employ advanced workforce management systems to optimize response times during outages and ensure efficient deployment of repair crews. Weak grids often face a shortage of skilled labor, resulting in poor maintenance, delayed repairs, and inefficient grid management. Training programs may be outdated or insufficient. Weak grids invest little in R&D, which prevents the adoption of modern technologies and innovative solutions for improving grid stability and efficiency. Weak grids are often isolated from international knowledge-sharing networks, leading to slower adoption of best practices and advanced technologies. Workforce management is typically reactive rather than proactive, with crews dispatched after problems occur, leading to longer outages and inefficiencies. Strong grids receive consistent investment in grid infrastructure, including transmission lines, substations, and smart grid technologies. This ensures that the grid remains reliable, resilient, and capable of handling growing demand. Strong grids have better access to domestic and international financing options, including public-private partnerships, green bonds, and international development funds. With a stable regulatory framework and clear long-term energy policies, strong grids create a favorable investment environment that attracts both domestic and foreign capital. Governments and private companies in strong grid regions invest heavily in innovation, including renewable energy technologies, grid digitalization, and energy storage systems. Weak grids suffer from chronic underinvestment in transmission and distribution infrastructure, leading to outdated, inefficient, and unreliable systems. Weak grids often struggle to access financing, either because of poor credit ratings, political instability, or lack of investor confidence. This leads to slower grid development and modernization. Weak grids present a high-risk environment for investors due to regulatory uncertainty, market instability, and political risks, which further deters investment. Weak grids receive little to no funding for innovation or research, leading to a reliance on outdated technologies and a failure to adopt new, more efficient energy solutions. Strong grids have the resources to integrate large-scale energy storage systems, such as lithium-ion batteries, pumped hydro, or compressed air energy storage, which help to balance supply and demand. Energy storage enables strong grids to store excess renewable energy from solar, wind and dispatch it when needed, improving grid reliability and supporting renewable energy goals. Energy storage systems in strong grids are often used for grid services like frequency regulation and voltage support, helping to maintain grid stability during periods of fluctuating demand. In some strong grids, consumers have access to grid-connected home energy storage systems e.g. Tesla Powerwalls, which increase grid resilience and allow consumers to manage their own energy use more efficiently. Weak grids typically lack energy storage infrastructure, which limits their ability to balance supply and demand or store surplus renewable energy. Without energy storage, weak grids are more prone to instability, as they cannot easily absorb fluctuations in renewable energy supply or respond to demand peaks. Weak grids are forced to curtail renewable energy generation because they lack the capacity to store surplus energy, leading to wasted clean energy potential. Consumers in weak grids rarely have access to home energy storage systems, reducing their ability to manage energy use during outages or store surplus energy from rooftop solar panels. Strong grids use advanced load forecasting tools that rely on machine learning, big data, and real-time analytics to predict demand and ensure that the grid is adequately prepared to meet changing loads. Strong grids implement DSM programs that encourage consumers to reduce their energy consumption during peak hours, helping to balance supply and demand and reduce strain on the grid. Real-time demand response programs allow strong grids to adjust demand in real time by offering incentives to consumers to reduce usage during peak periods, improving grid stability and reducing the need for peaker plants. Strong grids often have widespread smart meter deployment, enabling utilities to gather detailed usage data and enhance demand management capabilities. Weak grids often rely on outdated or manual load forecasting techniques, resulting in frequent imbalances between supply and demand and increasing the risk of blackouts. Weak grids have little capacity for demand-side management programs, leaving them vulnerable to demand spikes that can overload the system and cause outages. Due to technological limitations, weak grids do not have real-time demand response capabilities, making it harder to manage demand during critical periods. Weak grids generally lack smart meter infrastructure, which limits the ability of utilities to collect detailed consumption data and hinders effective load management. Strong grids use advanced fault detection technologies like phasor measurement units and SCADA systems to quickly identify the location and cause of outages, speeding up restoration times. Automated systems in strong grids can isolate faults and restore power to unaffected areas within seconds or minutes, reducing the impact of blackouts on consumers. Strong grids have built-in redundancies and backup power systems e.g. backup generators, microgrids that ensure power is restored quickly after a failure. Strong grids typically have well-developed emergency response plans that coordinate utilities, government agencies, and repair crews to restore power efficiently after widespread blackouts. Weak grids often rely on manual methods for fault detection, which can take hours or days to identify the cause of an outage, leading to longer blackout durations. Weak grids have minimal automation, meaning that most restoration efforts rely on manual intervention by repair crews, which extends blackout recovery times. Weak grids lack widespread backup systems, forcing consumers to rely on personal backup generators during outages, which can be costly and inefficient. Weak grids often lack coordinated blackout management and restoration plans, leading to confusion and delays in restoring power after major outages.